Right, so a look at these data to get the ball rolling today with this lesson, which is all about the perfect ionic model. So by all means, pause the video for as long as you need to have a go at picking out any trends that you can find here, because I'm going to go straight into pointing out the trends for myself. So hopefully you can beat me to it. Anyway, so here we go. Well, what have we got here? When you read it carefully, you can see we're talking about the lattice energy. So the enthalpy change when 1 mole of an ionic substance is fully broken apart to form gaseous ions. So these energies represent the strength of the ionic bonding in the substance that we're talking about. We don't use bond enthalpies in ionic, we use lattice enthalpies instead because of the way that they exist in these sort of three-dimensional lattices, so it makes more sense. Anyway, as you can also see though, it's not just about lattice enthalpy, there's a comparison to be made here. Experimental. Now let's assume that these experiments are absolutely true and correct. So we're not talking about experimental error here and such uncertainties. We're talking about, let's say that this is the true, but the actual value. And then it's from a model of some sort, some kind of computer model. We'll have a look at the details shortly. So the model, you can take that to be like a predicted based on a few assumptions. And the experiment is reality, let's call it that. And you can see that they've been quantified in difference. Now, I'm not going to pay attention to this trend booking 2% here, sodium bromide, not interested in that. In fact, I'm not even sure if that's correct now I think about it. But we're going to see that with the ignoring NABR, there's a general trend here. There's a couple of trends. Now, something else that you'll need a bit of help with, it might not be obvious because silver's in a much lower period than sodium. I think just trust me on it for now is the safest way to play this. But Ag plus is actually smaller than Na plus. We'll see how that becomes useful in a moment. But we do know already that iodide is much bigger than chloride because it's got a whole couple of extra shells. So that it's clearly then I'm mentioning size here, size of ions. So here's another question for you really, because there's a lot of sort of unknowns here from your point of view, I imagine, unless you were in the lesson today. What are the variables that affect the strength of ionic bonding in an ionic substance? What would the variables be? Again, pause if you want a bit of time to think. Well, I'd say the magnitude of the charge for a start. A 2+ ion is more attractive to any negative ion than a 1+ ion and so forth. Secondly, the size of the ion. And there's two things in that. For a start, there's the distance between one ion and the next. So a big fat iodide is going to be further away on average, the center of it's going to be further away from its nearest positive ions than a smaller fluoride, for example, because of the size of the atom. So the distance between, and then also actually how spread out or how diffuse that positive or negative charge is in the ion. That's also a factor that we'll consider. So I think the best thing to do is jump in and show you, because I think if you try and work it out from scratch, you'll spend a very long time probably getting quite confused. But just before we move on, let's just take a few observations with us. If we just pick on the silver salts for now, silver chloride, bromide, iodide, whichever trend we're looking at from the model, which means predicted, or in reality from experiment, either way, as you go down group 7, as those negative halide ions get bigger, the ionic lattice strength gets weaker. Secondly, we'll just take a quick side-by-side comparison. The sodiums with the silvers. Again, I'm going to have to ignore the sodium bromide anomaly there. Generally speaking, silver halides have got higher or stronger lattice enthalpies than the sodium halides. Interesting observation. But this is the bit we haven't really touched on yet. How much of a disagreement there is. Now, yet another thing to note here. The predicted value for enthalpy of lattice dissociation is always less than that which it turns out to actually be. But the biggest disagreement is in silver iodide here. 10% stronger lattice energy, more energy required to overcome all the ionic forces, well, all the bonding, I better not say ionic forces, all the bonding in this substance than predicted. And for some reason, the model is more inaccurate with silver iodide than it was with sodium iodide or with sodium chloride. So let's push forward. Let's see how this all pieces together. So the perfect ionic model is your title if you're taking notes into your books at this point. Don't worry about the spec there, that's the old spec anyway, but it's identical to what we're doing. Now there's going to be a bit of clicking forwards and backwards through slides in this presentation. So you don't necessarily need to write all of this down if you're working from home. All right, let's just take it as a reminder, listen, and you'll see when the really important bits come up. You can always rewatch it and just go and find the bit, that you'd like to copy down into your notes if that's how you're going to work it. So we can do actual experiments, or we can just predict by theory then how strong how strong a lattice energy should be. We can use a bit of a computer model. We call it the perfect ionic model, using something called the Born-Londe equation to put a value on it. Or we can do series of experiments, and again, some of these might be not sort of lab-based experiments as much as like very high energy instrumental analysis sort of experiments. We can get values for enthalpy of atomization, of ionizations and such, and put those values into a Born-Haber cycle to get lattice energy out, and that could be dissociation or formation, same number, different signs. Now, what we saw in those data was that the predicted value for the lattice enthalpy was invariably less than the actual value. What that suggests is that there's some kind of additional bonding in lattice that the Ionic model, and again, I appreciate I haven't yet presented how it's calculated. I don't have to present it to you, but I will anyway. For whatever this model is, it always underestimates, but we saw that it underestimates worse in some cases than others. So for example, then there we are, silver iodide, lattice dissociation, so-called true value, 889 kilojoules per mole, have to be invested in, that's 889 kilojoules of heat, put into a mole of silver iodide in order to turn solid to gaseous ions. And you can see that the predicted value is about 10% less than that. It's always less when you predict. Now, that model then, the perfect ionic model, let's have a quick look at that. So the assumption that we make when we use a calculation to predict the strength of the ionic bonding in a substance is that for a start, the ions are perfectly spherical. We could also call them point charges, which means like infinitely small points in space relative to other points in space around them in a lattice formation, which are just electrostatically interacting with the ones around. So we either assume they're point charges or we just assume they're little spheres of varying sizes. Now, don't panic, right? The Born-Londe equation, this is not on the spec, but I wanted you to see it. We just call it the perfect ionic model and say the predictions makes these assumptions. Let's have a look at those assumptions in a formula. We're not going to dwell on this for too long. E, we'd call that delta HLD, enthalpy of lattice dissociation. Na, Avogadro, that's going to give us the per mole unit because Na is 6.02 times 10 to the 23 mole to the -1, i.e. that many things per mole. So there's the mole in kilojoules per mole. M's the Madelung constant. We don't even look into any of that at all. This ionic lattice structure here, that's what we call face-centered cubic. That's just one of many ionic crystal packing structures. There are many others. This is how magnesium oxide, I think, definitely NaCl. This is how those ions are packed into a lattice. But they could be offset slightly. They could be like, bricks in a wall kind of overlapping, but only half covering each other. There are all sorts of different three-dimensional arrangements. Imagine if we had something like magnesium chloride. You've got two negative ions, one positive ion. So they wouldn't pack into a structure exactly like this. If you're interested, go and look up ionic crystal structures and you'll see all sorts of interesting arrangements. Anyway, the assumption is that they fit together in particular ways, which is true. We can find out what the packing structure is using a technique called X-ray diffraction. We blast X-rays through a sample and we basically find out how the atoms are organised. So that's something we can deduce. The Madelung constant is a numerical way of accounting for the various different crystal structures. Moving on from that now. Z plus and Z minus, those are our charges. So in NaCl, Z plus is 1, Z minus is 1, 1 plus and 1 minus. In magnesium chloride, Z plus is 2 because it's a 2 plus ion. Z minus is minus what is 1 because the negative ions are singly charged. There are two of them, but that's a separate matter. We've got there the charge of an electron with the elementary charge. So there's a way of anyway. We're not going to worry about this now. And along the bottom here, again, now you've got 4 pi in there. There's well, you can see it's all accounted for already, but that's basically looking at the sort of, well, I don't want to go into too much here. The sort of radial, the assumption that the attractions are all acting in equal force and in every direction. So we imagine that those positive ions are emitting, they're not emitting at all, but are exerting the sort of identical attractive force in every direction, all around spherically, to the nearby ions, and the negative ions are doing a similar thing. Then we've also got distance in there, so we've got R naught, distance to closest ion. That'd be nucleus to nucleus distance. So in other words, when we really boil this down, and we better move on now, Born-Landay equation, the perfect ionic model, calculates delta H lattice by accounting for a number of factors, primarily, well, amongst which are charge and distance, okay? But this is all working on the assumption that that's it, it's purely electrostatic. These particles never meet, these ionic ions never actually have contact. They're discrete, they're separate, and they're exerting an electrostatic force over a certain distance and a certain amount of attractive force. Moving on then, so back to our spec, here we go again. So the perfect ionic model makes those assumptions that we've just discussed. It assumes they're point charges, or we're going to say instead perfect spherical objects, and that they exert the same, they work the same force in every direction, and that's spherically all around. The thing is, that's not quite right. As we've seen, the experimental data, and this is besides the problem of experimental uncertainty, let's just assume those results were absolutely perfect. It's always the case that the experimental data show that there's a bit stronger bonding in the lattice than predicted. There must be some additional bonding, and you can see the term there that's been highlighted in blue, covalent character. Now, pretty well, all ionic substances have some covalent character. When we did bonding back in the start of year 12 or early on, we talked about how it's not really right to categorize covalent, ionic, metallic and phylyl chemicals into one of those three categories in terms of what type of bonding they exhibit. And actually ionic substances have some covalent character. Now we've seen the flip of this already. We did electronegativity. That was talking about covalent substances, so not relevant here. But we talked about molecules like H2O and HF as polar molecules. And we could have said that those were covalent molecules with some ionic character. They've got partial charges. They're not ionic, but they've got some ionic character. Here we've flipped it around again. Here we've got ionic substances with some covalent character. So before we move on again, let's just think, what would covalent character be? Well, a covalent bond is a shared pair of electrons. So covalent character must be something to do with electron sharing, but it's nowhere near a full shared pair of electrons. Just like the delta plus on H2O hydrogen is nowhere near a full 1 plus charge. But it's got character, it's got some of it. So, onto this diagram then. Now, NaCl. NaCl is a pretty ionic chemical. We saw in the example before that the predicted value and the experimental, let's call true value, were only about 2.3% apart. That means that there's only about 2.3% discrepancy between predicted and actual, which means most of what's predicted by the Born-Landay equation is correct. In other words, the ionic bonding is predicted correctly and there's not much additional covalent character. We haven't really still got to what that looks like, but we're getting there in a minute. So NaCl, here we've got an electron diffraction type diagram. You can imagine this as like a photograph. Obviously it's not a photograph, but it's that kind of idea. This is a pretty realistic representation of the shapes of the ions in the lattice. We can see that they're not perfectly spherical, however they are pretty round. This is a two-dimensional slice through one. You could probably rotate that in every direction to get an idea of what it would be like in 3D, but they're pretty spherical, they're quite round, and they're discrete, so we're not seeing much overlap here at all between ions, but they will be having impact on each other than ionic interactions. Now let's look at an extreme example. Let's go to silver iodide. So back to this table briefly, NaCl, 2.3% difference. The model, which is based on purely electrostatic interactions between these point charges or these spherical ions, exerting their force in every direction equally to the surrounding oppositely charged ions, pretty decent agreement. Down here though, AgI, why is it so much more different? Why is there an additional 10% of bonding effectively in the lattice of AgI compared with what we saw in NaCl? Well, the thing here is it's all about size really. What we have in silver iodide is a relatively small positive ion and matched up to that a rather large negative ion. So we're going to talk about distortion, which we could also call polarization here, and those two words we're going to use interchangeably. So in the ionic lattice, the Born-Landay equation, the perfect ionic model, would assume that that's how they are. They're perfectly spherical, they're discrete, and they're interacting by electrostatic forces only. However, What we have in the case of silver iodide is this small positively charged ion like distorting the electron shells of the negative ion. So this big juicy iodide ion comes along, and the silver that's on every side of it, I've only shown one here, but there'd be another silver up there, another there potentially, each distorting this. So this would be more like a plus shape than an oval. But what the point we're making here is that there's so much electron distortion. Basically, the negative ion gets warped. You wouldn't recognize it as being a spherical ion, and it leads to the outer shells slightly overlapping. Now, that's not a shared pair of electrons by any means. It's not a formal covalent bond, but what it is some electron density overlapping. Remember that we know that electrons we can be thought of as being fuzzy. Well, the orbitals that they occupy are fuzzy and not very well bounded or not very well defined at the boundaries. And so we've got here some fuzzy overlap basically between the two outer shells. That sounds a lot like electron sharing. That sounds a lot like covalency to me. But since it isn't a full covalent bond, we just call it covalent character. So there it is. Now that covalent character goes on top of the electrostatic interactions that are still there. So the silver iodide still has the electrostatic opposite charge attraction as predicted by the Born-Londé equation or the perfect ionic model. It still has that, but it has additional bonding, and it comes in the form of covalent type bonding, i.e. shared electron density. Now, we're not going to dwell on this slide too much. I didn't use this in class today, but just to bear in mind, basically, the ions have different sizes. I think that's all we need to say for now. Moving on. Now, covalent character then. Well, here's a sort of list of when it happens the most. So you get more polarization or distortion of the negative ions when you've got big, juicy negative ions, particularly lower down the group 7, so iodide and bromide. But also those ions which are maybe a bit smaller, like oxide, but which have got more negative charge to be pulled away. So something like O2 minus, Cl minus, particularly I minus, yeah, very, very polarizable. Also, there's the substance that does, the particle that does the polarizing. So big juicy anions are only part of the picture here. You need something that's going to cause their distortion. So the bigger the anion, the easier it is to distort, but you need something to polarize it in the first place. And that's where small, very concentrated points of positive charge come in. So the really extreme examples would be aluminium and beryllium 2 and 3 and 2 plus respectively. They're both period 3 elements. In fact, sorry, beryllium's in period 2 even. Be2 plus is tiny. It's got the same electronic configuration as helium. It's got one shell. On top of that, it's got many more protons than helium. It's got 4 protons, twice as many. So that's a really positive ion squeezed into a tiny, tiny little volume. Aluminium, it's 3 plus. That's almost as high as you'll get. And what we see here is that these really small, concentrated points of positive charge, well, we can define their sort of nature as having a high charge to size ratio. Charge is high, relatively speaking. It's 1, 2, or 3 plus. Typically, you can have 4 plus, but it's unusual, apart from in something like titanium, maybe. And size, well, that's volume. You know, we're talking volume of a sphere there, basically. The assumption being that they're spherical. But it's not just those highly charged, very tiny ions that will do polarization. So Na plus, K plus, Cs plus, they've all got the potential to polarize, but some are just much worse than others. So what is this covalent character? Well, we've already talked about this really, but it's a small positive ion interacting electrostatically with a large negative ion. And the large negative ion's electron cloud gets pulled towards the positive ion. And in the lattice, that's been pulled in every direction that there is where there's a positive ion to be pulled towards. And what we end up with is overlap of the electron density between the ions. And so on top of the electrostatic attractions that are there, we've got this additional bonding, which we call covalent character. Hopefully I've said enough about that. So there isn't much left to say. I've already talked about additional bonding there, or covalent character adding to the strength of the lattice. There isn't much more to say now, so really the next couple of slides are just a few examples to illustrate the idea. Now this is something again that if you're in my class we looked at in passing and as extra when we looked at bonding, and we sort of left it half done really because we talked about this, then we went to look at electronegativity, and now we come back with a bit of experience. We're not going to spend hours looking at this now either, this Van Arkel triangle, but I just want to point out that at the top there you've got CSF, cesium fluoride. the most ionic substance. Remember that this is a continuum between covalent and ionic. We're really working along that right-hand edge of the triangle here when we think about this. Cesium fluoride has got the least covalent character, because what you've got there is the total opposite of what you would need to get more covalent character. We've got a big juicy positive ion. So that positive charge in a big cesium ion is very diffuse. It's not concentrated into a small space like in Al3 plus or anything in between. So cesium plus is really not very polarizing at all. And on top of that, here it's coupled up with fluoride F minus. It's a very small negative ion. Now fluorine's the most electronegative element. Here we're talking about F minus, the particle it's got a full outer shell. But the fluorine nucleus, the fact that it's the most electronegative element, that tells us that the attraction between the nucleus and its outer shell electrons, or its outer shell in general then, is very strong. And that follows here then that fluoride is difficult to distort. You're going to have trouble pulling the electrons out of shape. We're not talking about pulling them away. We're not talking about oxidizing it, taking electrons out. We're just saying like it's really small, it's difficult to distort. So CSF is like the wrong way around for covalent character. What you'd want instead is a tiny positive ion and a big juicy negative ion. We've got the opposite here. As we go along this continuum from ionic to covalent, from the top to the bottom right corner, we're getting more covalent. And again, just to remind you that we talked about electronegativity in the past, and if I pick NF3 or H2O's there, HF as well, those are polar molecules. Those are molecular, which means they're covalent. They don't exist in ionic lattices, but they've got partial charges. They've got delta plus, delta minus. So those are covalent with ionic character. And if I picked out something that's not actually plotted on here, but something like a silver iodide, we talk about an ionic substance with covalent character, the kind of other way around. We're not paying any attention to metallic character, but if you're really interested, that would be something to do with like superconductors or semiconductors, actually more likely semiconductors. That'd be more to do with the delocalization of electrons through the structure. Moving on again. So we saw the silver iodide example. Let's have a quick look at one or two others. Clickety click, here we go. Well, sodium bromide, not a massive difference there. Sodium hasn't got a lot of power to distort bromide. Even though bromide's quite susceptible, it's a reasonably large negative ion. That negative charge isn't really tightly held onto by the nucleus because of all the shells. But Na plus isn't a great distorter. Silver plus is smaller, you see, which might seem unusual because it's lower down the periodic table, but it is smaller. So again, these are just examples, so we're just going to click through these. Now here's a good example, aluminium chloride. This has got so much covalent character, it's actually covalent. So AlCl3 is actually a molecular substance. It's got a relatively low boiling point with weak intermolecular forces, van der Waals forces, rather than and dipole-dipole. It's not even ionic, it's actually a fully covalent molecule. So it's molecular, which means it doesn't exist in an ionic lattice. So aluminium is so polarizing that the most stable outcome for Al and Cl to come together in is actually not as an ionic lattice, but as a covalently bonded molecule. So that's quite an unusual example. And there's a nice illustration that idea of metals and non-metals, it must be ionic, actually isn't correct. That's all there is to say then. So hopefully that's illustrated the idea. By all means, go back and pause on some of the notes if you need a bit more time to scribble them down, if that's what you're doing. But it comes down to small positive ions, large negative ions, distortion, overlap, and therefore additional bonding, which is on top of the electrostatic attraction. This example that we're finishing on here doesn't actually have any electrostatic, like ionic type attraction, because there aren't any oppositely charged ions in the first place. There you go. Hopefully that's helpful.